Okay, back with the second part of the mean value theorem. The first part of this, the first video focused on the hypothesis, which was that the function needed to be not only continuous on the closed interval, but differentiable on the open interval, okay, from A to B. We needed that differentiability. If we had a point in the middle, which there was the function was not differentiable, well, then all bets were off. But here's a case where the function is continuous and differentiable, so the mean value theorem will guarantee something for us, right? What does it guarantee? Well, it guarantees the conclusion of our theorem there. What does it say? Well, it says that the average rate of change, remember that from way back in September? The average rate of change, that was the secant, the slope of the secant line, all right? So if we were to draw the secant line, here's f of a up here, and there's f of b right there. So we're going to draw that secant line best I can, didn't do it all that well. That line right there has a slope, because all lines have a slope, unless it's vertical. So it's got a slope, and it's equal to, if you recall, I'm writing this right in the glare again, I apologize for that, f of b minus f of a over b minus a. Okay, that was the average rate of change of a function over a closed interval from a to b. It's a slope formula that you've been doing since Algebra 1, or even middle school, okay? It's the slope of that blue line right there. And that's our average rate of change. Well, the mean value theorem says, guess what? If you've got this average rate of change, this slope of the secant line, there's going to be an instantaneous rate of change. Remember, that's the slope of the tangent line, all right, other words known as the derivative. There's going to be an instantaneous rate of change that will happen somewhere in between, which is going to be equal to this, okay? Now, think about this. If the two are equal, and they're both slopes, what do we know about slopes that are equal? Two lines that have equal slopes. Those lines are known as parallel lines. Yes. So what it's basically saying is, guess what? There's going to be a spot, and it looks like eyeballing it, it's going to be right around there, where if we draw this tangent line to the curve, okay, that tangent line is also going to have a slope. Okay, and the slopes are going to be the same, because the lines are parallel. All right, but remember, this is the slope of the tangent line. What is the slope of the tangent to the curve at a point? Yes, the derivative. All right, so this slope is the derivative. Okay, specifically, it's the derivative at a point. This point right here. This point doesn't have a label yet, so let's label it. And the label that we see in the theorem on your paper is C. So the slope of the brown line is f prime of C. The slope of the blue line is f of b minus f of a over b minus a. But the slopes are equal because the lines are parallel. So what does the theorem say? Well, it says that f prime of c is equal to f of b minus f of a over b minus a. That's your mean value theorem. And basically all it's saying is that, guess what? We can find a tangent line that has a slope which is equal to the slope of the secant line. Now finding the slope of that brown line might be difficult, because if we don't have a function, how can we derive it? Okay, but if we have points, we can find the slope of the blue line. All we need are points. We don't need the actual function, because we're just doing f of b minus f of a over b minus a. We can find this one real easy, and this one might be hard to find, but we don't have to find it, because if we find this one, well, this one is equal to that one by the mean value theorem. Okay, this goes back to the trip. Okay, here's I know it's not a graph of a trip, but I think I used the number 53 miles per hour. So the average, the slope, the average rate of change, the average velocity of your car was 53 miles per hour during the trip. Well, the mean value theorem says that at some point during that trip, you must have gone 53 miles per hour. Now, in all likelihood, you did it more than once, okay? But you had to have done it at least once, okay? And that's where our mean value theorem comes into play. It helps us determine stuff about the derivative where we may not know anything about the derivative, but we can find it because of the mean value theorem and our ability to easily grab the average rate of change. Remember, that was a real easy homework assignment. You guys liked that because you could get the answers real quick, because ultimately you were just doing algebra. Okay, so the mean value theorem says that, guess what? The derivative of the function, which we may not know anything about, at some point in the interval, because remember, c has to be between these two, the derivative at some point will be equal to the slope of the secant line. Okay, so the homework assignment involving the intermediate mean value theorem is a double-sided sheet here. And basically on the front with problem number 2, I'm asking you, is the hypothesis of the mean value theorem, does it put the mean value theorem into play? Do we have a situation like this where the function is differentiable, or do we have a situation like this one down here, and I changed it from f to g just to keep them separate, where the function is not differentiable? Because if we look at this real quick, let me draw the lines again. Okay, so we've got blue, there's A, rather f of A, there's f of B. I'm going to draw that secant line. Hopefully that appears on your screen. I know it's kind of light, but there's line. So can I draw a tangent line to this curve which is parallel to this blue line? And the answer is no, because this sharp point is screwing everything up. If I pick a point up here, like that one, well, my tangent line does this. If I pick a point like this one right here, my tangent line does that. Neither of these brown lines is parallel to the blue line. Okay? It won't work. Why? Because the point where the function is not differentiable screws everything up. That's why the mean value theorem says, hey, listen, I will guarantee this, but in order for me to guarantee this, I need a continuous function and a differentiable function. And if I've got that, good. We are good to go. I guarantee this will happen. But if I don't have a differentiable function, then all bets are off. It might happen, but I don't guarantee it. Okay? It's like when you jailbreak your iPhone. Okay? Well, now Apple says, guess what? You opened that up. We don't cover it anymore. Okay? We might be able to fix it, but we're not covering it because you broke it open. Okay? So that's basically what's happening right here. This non-differentiable point is breaking everything open. Okay, so just quickly now, on the exam, you could be expected to be tested on the mean value theorem in 2 different ways. One way in which they will look to test you is whether or not the mean value theorem is eligible. Okay, they'll say something like, hey, guess what? The average rate of change of this function g from a to b is, I don't know, let's look like it's like maybe negative 1/7. Is negative 1/7. Does the mean value theorem guarantee that their derivative of g will equal 1/7 for some spot between a and b? And you have to look at that and you have to say, no, it does not. Why not? Because g prime doesn't exist at this point. So therefore, the hypothesis cannot be met. So they give you eligibility questions like that. Okay? At the same time, they may also give you conclusion questions where they'll say, why is it true that f prime will be equal to negative 2/3 for some value between a and b? And you have to think, okay, why is it true? Well, it's true. I don't know it. I have a graph of f. How am I supposed to figure out f prime? Well, you can do an average rate of change. And again, these values will be given to you. And let's say you do an average rate of change based off these values, and you get an answer of negative 2/3. Well, the mean value theorem guarantees that the derivative must also be equal to negative 2/3. And again, we found the negative 2/3 because we did a nice, easy average rate of change. So these mean value theorems are based off of 2 things. A, could you find or recognize points where the function is not differentiable, and then use that information to explain why the conclusion, or rather the hypothesis, is not valid? Or B, do you understand that, hey, if the hypothesis is valid, and they ask you a question about f prime, even though you don't have the graph of f prime, do you understand that the conclusion of the mean value theorem says, guess what? Do an average rate of change, something that's easy, get the answer through the average rate of change, and then apply it to the derivative because the mean value theorem says you're allowed to do that since the hypothesis was met.